Good morning, students. Today we will start section 1 of functional analysis. So our first topic in this section is normed linear space. In order to define normed linear space, first of all we define norm. So let us take a vector space X and define a function from the vector space X into the space of real numbers such that the following conditions are satisfied. The first condition is the norm of X is greater than or equal to 0 for every element X belonging to the vector space X. It means norm is non-negative. Second property, norm of every element X belonging to the vector space X is 0 if and only if the element itself is 0. Next property, for a scalar lambda belonging to the field of scalars and this X belonging to the vector space X, norm of lambda X is equal to lambda mod into norm of X. This property is called absolute homogeneous property. And the last property is triangle inequality. For every two elements X and Y belonging to the vector space X, X plus Y norm is less than or equal to X norm plus Y norm. So if these conditions are satisfied, then we say that the function defined from the vector space X into the vector space R is norm on the vector space X, and the corresponding ordered pair formed with X with this norm, that is called normed linear space. Let us see some examples of norm. So the first example is, we'll prove that the vector space of real numbers, that is normed linear space. So we already know, because the vector space of real numbers, the space of real numbers, that is a vector space over itself. So it remains to prove that it is norm space. In order to prove this is norm space, let us define norm on the set of real numbers. So let us define the function from the set of real numbers to itself by X norm is equal to mod of X, where this X belongs to the set of real numbers. Now we will verify the conditions of norm. So the first condition is norm should be non-negative. Now norm of X, as we have defined, this is X mod, and we already know mod is always non-negative. So this is greater than or equal to 0. So first property is satisfied. In the second property, we prove that norm is 0 if and only if the element itself is 0. So let us take norm of X is 0. Now by our definition, norm of X means mod X. So mod X is 0 because mod is also non-negative quantity. So if mod X is 0, if and only if the element itself is 0. Now the next property, let us take lambda a scalar and X is a real number, and let us find lambda X norm. Now by using again this definition, norm of lambda X is equal to mod of lambda X, and this can further be written as lambda mod into X mod. Now X mod is equal to norm of X. So we have proved the property norm of lambda X is equal to mod of lambda into X norm. Now last property, triangle inequality. Let us take X and Y, two real numbers, and we find X plus Y norm. Now by our definition, X plus Y norm, that will be X plus Y mod. Now by using the triangle inequality in the set of real numbers, this is less than or equal to X mod plus Y mod. Now X mod is norm of X and Y mod is norm of Y. So we have proved all the four conditions for norm. So this proves that the set of real numbers, that is a normed linear space with norm defined by norm of x is equal to mod x. In the same way, you can prove that the set of complex numbers that also forms a normed linear space with norm defined by norm of z is equal to z mod. Here z is a complex number. You can prove this in the same way as we have proved in the case of set of real numbers. Now, next we will discuss further some examples of normed linear spaces. So the next example is Euclidean space. Euclidean space means n-dimensional space of real numbers that is a normed linear space. So in order to prove this, now what is Euclidean space? By definition, Euclidean space is the set of all the n-dimensional real numbers, means the elements of the type having the n coordinates x1, x2, x3 up to xn. Here these x1, x2, x3 up to xn, these are the real numbers. Now we will verify the 4 properties of norm. So in order to verify them, firstly let us define norm on the Euclidean space. In order to define norm, let us take an element x from Rn Euclidean space and we define norm of x is equal to the magnitude, or we can say modulus of this element x, which is given by x1 square plus x2 square plus x3 square and so on up to xn square under root. So we can define norm of x is equal to summation xi mod square under root. And the Euclidean space is a vector space under the operations of addition and scalar multiplication. Now let us verify the properties of norm. First property, we have to prove norm is non-negative. Now by definition of norm x, you can see from here, because these quantities are non-negative and so their sum will also be non-negative. So this whole expression, this is non-negative. So we can say that norm of x is non-negative. Next property, norm is 0 if and only if this expression is 0. Now because this expression is 0, so from here we get summation xi mod square is 0. Now because these are non-negative quantities, if the sum of non-negative quantities are 0, then each quantity is individually 0. So each xi will be 0 for every I, where I varies from 1 to n. And now x1 is 0, x2 is 0 and so on up to xn is also 0. So we can say that x is 0. So this proves the second property, that norm x is 0 if and only if the element x itself is 0. Now the next property, absolute homogeneous property. Let us take the scalar lambda and the element x belonging to the Euclidean space Rn. Now let us find norm of lambda x. Now again by definition of norm, this is given by summation lambda xi mod square root. Now lambda is a scalar, so lambda square under root, that will give us lambda mod, and inside we have summation I varies from 1 to n xi mod square under root. Now this is norm of x. So we get lambda x norm is equal to lambda mod into x norm. Now the next property, triangle inequality. Let us take x and y belonging to the Euclidean space Rn. Now let us find x plus y norm. Again by using the definition of norm, this is given by summation xi plus yi mod square under root. Now we will use Minkowski inequality, which is the Minkowski inequalities for sums, which is given by, if we take two elements x and y belonging to LP space, these are having the coordinates x is having the coordinates xi and y is having the coordinates yi. So then according to this inequality, we have summation xi plus yi mod raised to the power p whole raised to the power 1 by p. This is less than or equal to summation xk mod p whole raised to the power 1 by p plus summation ym mod p whole raised to the power 1 by p. So here we can use this inequality. Now here p is 2. So taking p2 here, this will be less than or equal to summation xi mod square under root plus summation yi mod square under root. Now by definition, this is x norm and this is y norm. So we have proved all the properties of norm, and this proves that the Euclidean space, that is a normed linear space. Now next we prove that every normed linear space is a metric space. Now in order to prove it a metric space, first of all we will have to define our distance function, or we can say metric, on this space. So let us take n be the normed linear space, and let us define a function d from n cross n into r by the distance between the two elements x and y of n is given by x minus y norm. So we have defined our distance function. Now we'll prove that this d is a metric on n. So let us verify the properties of metric. So first property is distance between x and y, that should be non-negative. Now because distance between x and y is x minus y norm, and by the properties we know that norm is non-negative. So we can say distance between x and y is greater than or equal to 0. Now next property, distance between x and y is 0 if and only if x and y are same. So let us take distance between x and y. Now this is x minus y norm. Now we know that norm is 0 if and only if the element itself is 0. So x minus y is 0 if and only if x is equal to y. This proves the second property of metric. Now the next property, symmetry, means distance between x, y is same as distance between y and x. So let us find the distance between x and y. By definition, distance between x and y is given by x minus y norm. Now we can take minus 1 common from here. This will become norm of minus 1 into y minus x. Now by using absolute homogeneous property, the mod of the scalar minus 1 into the norm of the vector y minus x. Now this is 1. So distance between x and y is y minus x norm, and by definition this is the distance between y and x. So this proves the symmetry. Next property is triangle inequality. We have to prove that if we take three elements x, y and z belonging to n, then distance between x and y is less than or equal to distance between xz plus distance between zy. So let us find the distance between x and y. Now by definition, distance between x and y is given by x minus y norm. Now adding and subtracting z and using the triangle inequality property of norm, this will be less than or equal to x minus z norm plus z minus y norm. Now by definition, x minus z norm means distance between x and z, and z minus y norm means distance between z and y. So all the properties for a metric are satisfied. So we can say that D is a metric on n. Thus we have proved that n is a metric space.